So good morning everyone. Just continuing with the next topic. So basic continuous time signals. So these are some basic time signals, continuous time signals which are used in signal processing quite often. The first one is the unit step function. The second one is the unit impulse function. Third one is the complex exponential function and sinusoidal signals. Unit step function we have in our last class already discussed. So if you have any signal like this, time and amplitude, and this step function usually it is having an amplitude of 1 and it starts from t equals to 0 and it is continuing till infinity. Then this kind of signals are regarded as unit step function. So we can also have a delayed unit function, a unit step function also. Okay. In the next case we have unit impulse function. In the unit impulse function we have already discussed about delta t, right? So what is delta t? Delta t is nothing but an impulse signal at t equals to 0. Okay. Now if we have some function like this, delta t minus k, so what happens? This function, if you see delta is there, that means it is an impulse function, but we are also having a summation of some numbers, right? So what are these? This is an equation for impulse strain function. Impulse strain function. So these are the impulse functions which are present at numerical integers. Okay. So where this is useful? This is useful during the sampling of the continuous time signals. Okay. So we have already discussed about this impulse strain and impulse function and unit step functions in our previous classes. So I'll be moving forward now. So this is the equation for the unit step function, and if there is any delayed unit step function, then it would be something like this. So this is the equation for the delayed unit step function. Now similarly, unit impulse function. So we all know at delta t not equals to 0 we are having 0, and t equals to 0 we are having an infinite a. However, the area of the direct function or the unit impulse function, it is 1, and hence we consider that the amplitude of the unit impulse function is 1. However, in practicality it is considered as 1. However, theoretically it should have an infinite infinite amplitude. Okay. So this is how an impulse function look, and this is the delayed impulse function. And the sampling property, as I was telling you, it is being when you multiply this impulse function with a continuous time signal, so at whatever location this impulse function is present, the output would be that particular value at that instance. Say for example, we are having a temperature versus time curve. So suppose at time small a we have a direct impulse. So what should be the output? We will be getting a single point at A, okay, over there. So when we talk about impulse strain, then At discrete times, you will be having these amplitudes like this. Okay. So this property is called the sampling, that with any given continuous time signal, when you multiply the direct impulse function or the impulse train, then at those specific locations where we are having the direct impulses, at those locations we will be getting the values of the whatever the variable is. Okay. Now the shifting property. So again, let us take that temperature versus time graph. So at initial location, at initial point, we have, say, impulse function at t equals to 0. So the resultant output we will be getting the x of 0. That means temperature at 0 time. Okay. Now suppose if I shift it to any other place, say at time equals to a, then when I have shifted the signal to this impulse function to time equal to a, we will be getting the value of x of a at that location. And this is what it has been denoted with this equation, integral of minus infinity to infinity ft, which is nothing but the xt, right, multiplied by delta t minus alpha dt, which gives us the alpha value. So by whatever fraction you are delaying the impulse function, at that location you will be getting the amplitude of the complex signal, of the continuous time signal, and at all other locations the values would be 0. Now coming to the complex exponential functions. So if you see the complex exponential function, it is given by xt equals to e to the power j omega naught t, and it can further be broken down into cos omega t plus j sin omega naught t. Okay, so you can have exponentially growing or exponentially decaying exponentially decaying signals, and this kind of signals, they are regarded as the complex exponential signals. Now you have the general complex exponential signals, which is given by xt equals to e to the power st, which can be again written as e to the power sigma plus j omega t. Okay, now this can again be rewritten as e to the power sigma t cos omega t plus j sin omega t. Now this form of the exponential function, it is regarded as the general exponential signal. Okay, whose real component is e to the power t sigma cos of omega t, and the imaginary part is e to the power sigma t sin omega t. Okay, now hearing the exponentially the signals are exponentially increasing when your sigma is greater than 0, and it is exponentially decreasing when sigma is less than 0. Okay, so you can see it in the previous slide. Now coming to the real exponential signals. So in the real exponential signals, what happens is that when this j omega component, it is being suppressed, that means it is having a this component is 0. Okay, so when this component is 0, this equation becomes xt equals to e to the power sigma t, where basically s is equal to sigma, which is a real number, and it reduces the general exponential general complex exponential signals into a real exponential signal. Again, over here, depending upon the values of the sigma, it can be exponentially growing or exponentially decreasing signal. Now coming to the sinusoidal signals. So sinusoidal signals, it is a kind of sinusoidal signal. Xt equals to a of cos of omega naught t plus theta, where a is the amplitude, omega naught is the radian frequency in the radian frequencies in radians per second, and theta is the phase angle in radian. Okay, and the fundamental period, it is given by t naught equals to 2 pi by omega naught. Okay, in our last class we have done some numericals. Basically in the discrete time domain it is basically the same. Okay, so from here 1 by t naught, it is equal to f0 in hertz, and this f0 it is regarded as the fundamental frequency. Okay, and this fundamental frequency, it is given by omega naught equals to 2 pi f naught. Okay, so this is an example of a continuous time sinusoidal signal. Now coming to the basic discrete time signals, the same thing, but in the discrete time domain we have the unit step function, unit impulse function, complex exponential sequences, sinusoidal sequences. So see, the same thing, from n equals to 0 to infinity you will be having an amplitude of 1, and it will go on. And then we can also have the signal in a delayed form, u of n minus k. Then unit impulse function, again if you see delta n equals to 1 for at n equals to 0 and 0 for n not equals to 0, and again you can shift it to any other position by varying the values of k. Now, just like the continuous time complex exponential signals, we have discrete time complex exponential sequences. You see over there, here and here. The rest of the things, they remain the same. And over here, if you see, omega naught by 2 pi equals to m by capital N, where m is a positive integer and n becomes periodic when it is a rational number, right? We have discussed in our previous class. Why you people are giving a blank face? Anyway, so again, general complex equation over here. So if you see c equals to 1, a equals to alpha equals to e to the power j omega naught, if you have it, then we can get a general complex exponential thing. And for the real exponential thing, this alpha should be both c and alpha, these should be reals. Okay. Now the sinusoidal sequences, again the same thing, xn equals to a of cos of omega naught n plus theta, where omega naught, it is the frequency and theta is the phase. Now coming to the systems. So what is a system? Okay, what is a system? A system is defined as a mathematical model of a physical process that relates the input signal to the output signals. Okay, say for example, we are having an inverting amplifier whose transfer function is t. We give a signal xt as the input and we get a signal yt as the output. Okay, so what happens in an inverting amplifier? Yt equals to minus v0 by v in into xt, right? Now what is this? This we call it as gain, which can also be written as t transfer function. Okay, so we can write it down, yt equals to t into x of t. Now see, this is what it has been written, y equals to t into x into t. Okay, y equals to capital T into x. Okay, so this capital T, it is the transfer function and this varies from system to system. So I have given the example of inverting amplifier. In the non-inverting amplifier, it would be it should be R2 by R1. No, आप लोग भी नहीं बता. R2 by R1, right? So in non-inverting amplifier, what it should be? 1 plus R2 by R1, right? So our transfer function, it becomes capital T. I hope all of you know about this gain of the inverting amplifier and non-inverting amplifier. Basic analog electronics class you must have done in your BTech level, right? You didn't do? Okay, then you have to go through the stuff. So it comes under biomedical instrumentation. Maybe the teacher will be teaching you. So the main thing is that what we want to say is that what is a system? A system is nothing but a mathematical model. In the case of non-inverting amplifier, 1 plus R2 by R1. So this mathematical model is for the non-inverting amplifier. For inverting amplifier, it is minus of R2 by R1. Okay, if you take this integrator, you will be having some mathematical model. So if you give some input, you will be having some output. And the most important thing is that your output is nothing but the multiplication of the transfer function with that of the input signal. Okay, so your input signal is getting multiplied so as to get an output. Okay, now these inverting amplifier or non-inverting amplifiers, we give a single input and we get a single output. So this kind of systems, they are regarded as single input single output system. Single input single output system. Similarly, if you think of the differential amplifier, where you give two different signals and you get a single output, they are regarded as multiple input single output systems. Okay, alternately, if you talk about the multi-parameter systems in a medical hospital, multi-parameter systems, what they are nothing but, if you see, if a patient is in the ICU, so what they will do, they will put all the sensors on the body. Say for example, SpO2 sensor would be there would be a PP sensor, there would be a heart rate monitoring sensor, there would be ECG electrodes, there would be respiratory probes attached near to the nose of the patient. So you are giving multiple input to the multi-parameter system, and you are getting an output which is having multiple, which are multiple in number. Okay, so if you are having this respiratory sensor, you will get the respiratory output. If you are having the ECG sensor, you will be getting the ECG output. Okay, so when you are having all this, so what is happening? Such kind of system, they are regarded as multiple input multiple output systems. Okay, now classification of the systems: continuous time and discrete time systems, systems with memory and without memory, causal and non-causal systems, linear systems and non-linear systems, time invariant and time varying systems, linear time invariant systems, LTI systems. Now these LTI systems, they are basically a combination of both linear systems and time invariant systems, and all biomedical signals usually which are used, not the what you call the AI powered or feedback systems, error minimizing systems, except those. Usually whatever the kind of amplifier we can think of, say for example the ECG processing system or EEG processing system, they are usually linear time invariant systems. Why linear time invariant systems? Because they are both linear system and they are also the time invariant system. Okay, then we have stable and unstable systems, and lastly the feedback systems. Now continuous time and discrete time system, what is the difference? The continuous time system, they would take input as the continuous time signals, and output that will be generated, they are also continuous time signals. Whereas in the discrete time systems, input is discrete, output is also discrete. Okay, systems with memory and without memory. Okay, so if you consider any systems with resistance, they are taking the input and they are just passing the signal to the output without any delay. So what I mean to say is that for the computation of the present input, present output, no previous inputs are taken into account. No previous inputs are taken into account. Whereas when we talk of the systems that are being developed using capacitors and inductors, what happens is that the present output, it is being affected by the past inputs also. Okay, so those kind of systems, they are regarded as memory systems. They are regarded as memory systems. Then comes the causal and non-causal systems. So say for example, this is the time and this is the amplitude here. So the current input, the current output, say at t equals to 0, it would be causal only and only when your all the signal components are towards the left hand side of the output signal. Okay, so what does that mean? That means the current output, it is only and only dependent on the past and the present inputs. Okay, they are the current output, it is only and only dependent on the past and the present inputs. Okay, say for example, if the signal, it starts at t equals to 1, what will happen? T equals to 0 is the present instance in our case. T equals to 1, it appears in the future. So if something appears in the future and if you are taking that into account for calculating the present input, then it is a non-causal system. Okay, so over here if you see, there are two equations which have been given. So say when y equals to y is 0, the t is 0, so for y0 we get x of 1. Okay, so y of -1, इसका मतलब है x of 0, and y of 1, इसका मतलब this means we have x of 2. In all the things, if you see, for 0, for y equals to 0, that means the present instance, we need to have a signal from the future. Similarly, at y equals to -1, again the signal needs to be from the future. Y equals to 1, again the signal has to be from the future. Okay, that means this system, it is non-causal. Okay, then let's consider the second one. Y equals to 0. Now y of 0 equals to x of -1, right? Oh, sorry, x of 0. Y of 1, x of minus 1, then y of minus 1, x of 1. Now in the first two cases, y equals to 0 is dependent on the input at the same time, so this should be a causal system. As per this, y1 mein we are taking the input from the x of minus 1, so again from here it should be a causal one. But in the last one, if you see y of minus 1, for the case of y of minus 1, it is taking input for x of 1, so this is non-causal. Okay, so which one should we take? So we have to consider the system as a whole. If a system is non-causal even at a particular period of time, that means the system is non-causal. Even if it is single point, it is non-causal, that means it is a non-causal system. So the second system, it is non-causal in nature. Okay. So again we are having these things. We have just discussed y of t equals to x of t plus 1. So it is a non-causal system. This one also we have just discussed. Okay. Yeah. So now coming to the linear and non-linear systems. So what is happening over here is that, say for example, we take the example of the non-inverting amplifier. So the gain over there, it is given by say 2. Okay. So in the first instance, what we do, we give a value of x as 1. So what should be the output we will be getting? We should be getting 2, say y1. x2 is 2, so y2, it would be 4. So y1 plus y2 equals to 6. Okay. Now say for example I add up x1 plus x2, so it comes out to be 3. Okay. Now what should be the y dash? So x dash equals to x1 plus x2. So what should be the y dash? So this is 3 multiplied by 2, that is again 6. Okay. Since your y1 plus y2 for the independent x1 and x2 is 6, and when you are combining both x1 and x2 and giving it as the input to the system, that is also 6, and since both say A and B both are same, these kind of systems, they are regarded as linear systems, and that is what it has been provided over here in this equation. This is the meaning of this equation. Okay. Now coming to the homogeneity or the scaling. So same thing, scaling में क्या है? Just a scalar quantity. Just a scalar quantity. So suppose I multiply this factor with say multiplied by 2. So my x2 dash, it becomes 4. So y2 dash, it would be 4 to the 8. Okay. Now if I take this 4, I multiply it with the again it is 8. So that is the scaling. So when you are multiplying the input with a scalar quantity, the whatever will be the output, and if you take the original input and get the output and again multiply the output with the system with the scalar quantity whatever we have taken, if both these things they are equal, then we can say that it is a homogeneous system. Okay. So by adding these two, additivity and the homogeneity or the scaling function, scaling property, if we combine these two, we get a condition which is regarded as superposition property. And this superposition property, what it says is that if I use a1x1 as the input and if I use a2x2 as the input, then my output, it should be a1y1 plus a2y2. Are you getting my point? यहाँ से आपको पता चल गया होगा? If you have understood the additivity and the homogeneity, then it should not be a problem for the superposition property. Any doubt? कुछ blank faces दिख रहे हैं? Okay? Done? Okay, very good. Now let's take some examples. So over here we have yt equals to t multiplied by xt. So suppose we have, when we have x1, so we get y1 which is equal to t into x1. x2, for x2 we get y2 t multiplied by x2. Okay, so y dash, it is equal to given by t into x1 plus x2. Okay, t equals to x1 plus x2. That means we are adding up these two numbers here. Okay, and y double dash is when we are adding up both the numbers, both the inputs, x1 plus x2. Okay, so if you see, C and D, they are equal. Since C and D are equal, it is a linear system. I gave you the example over here. First of all, what we did, we added the outputs. Okay, we added the outputs, and the second stage, what we did, we added the input and calculated the output. Right? Here also we have done the same thing. We got the equation. For x1, what should be the y1? We calculated that. For x2, what should be the y2? We calculated that. Then y dash is nothing but the addition of the y1 and y2. Right? And in the third case, y double dash, it is the addition of the inputs, and just in the place of the x we have put this addition. Now both of these should be equal. We have seen in the example here C and D are equal, right? So this is a linear system. Now coming to the next one, yt equals to x squared t. So x1 equal to x1, when you give x1 you get y1 equals to x1 square. You can also write it like this. For x2 you get y2 x squared 2 x2 square t, and then y dash, what you get, x1 square plus here multiplied by this thing. Okay, now look into this thing yt, what it should be. So what this is basically, x of t whole square. Now we have to change this input. So x1t plus x2t whole square. Are you getting my point? We are changing the input signal. We are changing the input signal. Previously we have added the output signals, this thing. So it is y1 was x1 square t, y2 was x square x2t x2 square t, right? So it was this one. But in the fourth stage we have to calculate when the input is changed. and when the input is changed, input is this one, x1t plus x2t whole square. Now here c and d, they are not equal, hence it is a non-linear system. Similarly, if you get into yt equals to xt square, this is very interesting to see. For x1 we get x1 t square, for y2 it is x2 t square. Okay, so y dash is x1 t square plus x2 t square. Y double dash also, it is x1 t square and x2 t square. Okay, why? Because x is a function of t square, you cannot change that. In the previous case, x is a function of t, and this is basically x, it was the square. Herein the square is within the t, so x is basically the function of the t square, so you cannot change that. So here your input is basically x1 t square plus of x2 t square, and that's why you have got this one. So this is a linear system, and this one we have already discussed in the previous slide, so I am not again continuing with that. Now coming to the time invariant and time varying system. Why do you need a time invariant and time varying system? This is because when we talk about the biomedical signals, so what happens, the systems should be time invariant. Why this time invariance is needed? Say for example, what happens in time invariant system, you have a system, if you give a signal now, you will be getting an output. Now if you delay the signal or advance the signal and then give the input to the to the system, what happens, regardless of the delay or the if you forget that, the nature of the output should be same. Otherwise what will happen, if you are analyzing something now and if you are analyzing after a certain period of time, both the analysis will be different. Okay, so whatever the output you are getting, that should not be dependent on time, and this is what is called time invariance. If the processing varies as you delay or advance the signal, or in other terms, if you shift the signal, then it is regarded as time varying system. However, we do not want a time varying system, we want only the time invariant system, because if by shifting any kind of signal, whether delaying or advancing, if the nature of the output changes, that means our analysis will be becoming incorrect. Okay, so this we need to understand. So let us take some example that will give you some understanding how to calculate this thing. So yt equals to t into xt. So first the signal is delayed, which is, and the output is given by y of t comma k, y of t comma k, which is equals to t multiplied by x of t minus k. That means the signal has been delayed. Okay, so yt comma k, it is the signal due to the delaying of the input, due to the delaying of the input. Okay, on the other hand, in the second case, we have to find out the output when the time is being tailored with t minus k. So when we go for the t minus k, so this will also change, okay, to t minus k and x of t minus k. So in the second case, t will be replaced with t minus k. In the first case, we were delaying the signal. In the first case, we were delaying the signal. In the second case, we are not delaying the signal. We are just replacing t with t minus k. Wherever we will find t, we will be replacing it with t minus k. If it is n, we will be replacing it with n minus k. Okay. So, after we do both of these, delayed output and by replacing time, delaying time, if we both 1 and 2, if they are varying, then the system is regarded as time varying system. In the second case, in the second example over here, yt equals to x square t. So delaying of the signal, see, same. When we are replacing t with t minus k, it is also the same. So this system, it is time invariant system. In the third case, yt equals to xt plus 5 of u of t. Okay. In the first case, we are delaying the input. So input is here. So input has been delayed, see. But this u of t, it is not a signal. It is not a, it is a signal. It is not an input signal. Okay. So since it is not an input signal, it will remain as it is. Whereas in the second case, where t will be replaced by t minus k, if you see, in all the cases it has been changed, and due to this reason 1 and 2 both are differing, and hence this system is a time invariant system. Time varying system. Okay, sorry. So it is a time varying system. Now coming to the last example of here, this section, time varying section, yt equals to x of t square. So yt equals to x of t square minus k, and here you are having t is being replaced with t minus k, so it becomes t minus k whole square, which again become time varying system. Okay, time varying system. So in the previous case, if you see in the over here, it was a linear system. Here it is time varying system. So combining these two, we can say this system is not an LTI system. Similarly, over here it is time invariant. Okay, but if you see over here, it is a non-linear system. So again, it is not an LTI system. So these two systems cannot be used for conventional biomedical signal processing techniques. Okay. So this is what linear time invariant systems. So they have to follow both the linearity and the time invariance principles. Now the stable systems. What are stable systems? So usually in biomedical systems or any other systems, there is a word called BIBO stability, bounded input, bounded output, stable. Say for example, again I will take the example of non-inverting amplifier. So you have an amplifier which you have designed. You give an input xi, you get yi. Okay. So if you give a finite input, you will be getting a finite output. If that is the case, that means the system what you have developed, it is a stable system. Okay. But however you say, over here the system is being operated at plus minus 12 volt, so the operation range is plus minus 10 volt. Okay. Now if you give 24 volt as the input, it is way above the operational range. So what the output you will be getting? You will be getting a saturated output. So that signal, 24-volt signal, it is not a bounded input signal. That means the system has not been designed to work in that particular range. Okay. So since the input itself is not bounded, your output is also not bounded. So your system is not stable for that particular system. So when we talk about the stability, that stability has to be within a particular boundary condition which you need to set. So that's why the stability is defined as the bounded input, bounded output, stable systems. That means if you give some finite input within the boundary conditions, you will get a finite output within the boundary conditions based on which you have designed the system. Okay, so this is what it has been written. Modulus of x should be less than equal to k1, which should be your boundary condition, and the corresponding the output is also bounded and defined by y less than equal to k2, which is again the higher limit of the boundary. Okay, and both this k1 and k2, they are the finite real constants. Now feedback systems. So it takes feedback from the present instance and it helps in the generation of the output. Say for example the integrator, or even the inverting amplifier, non-inverting amplifier, whatever you discuss. Okay, so if you see, so this is a non-inverting amplifier and it's given by right. So if you see, the output is taken into consideration to calculate the output itself. Okay, so this is the feedback loop. So from the output you are taking some information and you are putting it back into the system to compute the output itself. Those systems, they are regarded as the feedback systems. Okay. So with this we complete this chapter. From the next class we will be basically discussing about the Fourier series and Fourier transform.